To successfully evaluate trigonometric integrals, we would want to refresh some trigonometric identities first. So we're going to do it right now. Now, hopefully remember this basic Pythagorean identity, sine squared of x plus cosine squared of x equals 1. Well, remember that from that basic identity, we can obtain two more versions of it, right? If we get sine squared of x by itself, which means that I'll need to subtract cosine squared of x from each side. So that's sine squared of x equals 1 minus cosine squared of x, right? And then another version of that identity is when I decide to get cosine squared of x by itself. It means that I'm subtracting sine squared of x from each side. And I'll get cosine squared of x equals 1 minus sine squared of x. Okay, so we have those two. Now what else? Now from that basic Pythagorean identity, we can obtain another identity that relates secant and tangent. Remember, we do it by dividing every term by cosine squared of x. So if I divide 1 by cosine squared of x, I'm gonna get secant squared of x. If I divide cosine squared of x by itself, it's 1. And if I divide sine squared of x by cosine squared of x, I get tangent squared of x. Well, that's how we get this identity. Now from here, I can just rewrite it differently if I isolate tangent squared. So from that identity, tangent squared of x equals, well, I need to subtract 1, right, from each side. So it's going to be secant squared of x minus 1. Now, next one is very similar. So first of all, we obtain this identity from the basic one again, but this time if we divide every term by sine squared of x. So 1 over sine squared of x is cosecant squared of x. Sine squared over sine squared is 1. Cosine squared of x over sine squared of x is cotangent squared, right? So I can rewrite it with cotangent squared of x being isolated. It means that I'm subtracting 1 from each side, and I get cosecant squared of x minus 1. Okay, so we got that. Now, what else? You also might remember the half angle identity. It's one of the ways to write it, but we're gonna manipulate it a little bit so that we can rewrite it in a little bit different form. So this is what we're gonna do with it. I will rename a over 2. So a over 2, I'm gonna call x. So let a over 2 be equal x. Now, if a over 2 is x, then what is a? What is just a? Well, a is twice bigger than a over 2. Well, if a is twice bigger than a over 2, it means that this value is twice bigger than x. Well, it means that it's 2x. Right? And now I will also square both sides. So let a over 2 equal x, and then square both sides. So in other words, we will square sine of x on the left hand side, and we will square plus or minus square root of 1 minus cosine of x over 2. And that's what we'll get from here. So these were like the steps, but the final result will be the following. So the left hand side will be sine squared of x, and the right hand side, well, square cancel square root, positive and negative numbers squared, or positive and negative values squared become positive, so that's all gone, and I'm only left with 1 minus cosine of x over 2. 1 minus cosine of x over 2, like that. Actually, I can rewrite it, and that 2 in the denominator, it's same as 1/2, right? So I can also write like that, or sine squared of x equals 1/2 times 1 minus cosine of x, right? So that's the same thing, and that's what we're going to find helpful as we solve trigonometric integrals or evaluate them. Now the next identity can be manipulated exactly the same way, right? You can see that they're similar. It's just instead of sine on the left, I have cosine, and instead of negative sign here on the right hand side, I have positive sign, I have plus. So that means that I can right away write down its new version. So it's cosine squared of x equals, and I put 1/2 times 1 plus cosine. Oh, you know what? I made a mistake here, right? I should have written 2x here and 2x here. So let's fix that. I'm sorry. Let's fix that. 2x and then 2x, of course. I should have different angles on both sides. So it means that here it's also 2x. Okay, that's important. So please correct that in your notes. So that's a different version of that double angle formula. We will see how and where we'll use it. And finally, this double angle formula, that was half angle formula, now this is double angle formula. We can't really simplify it too much, but something that we might find helpful as we solve trigonometric integrals. We would need to have sine A cosine A or sine x cosine x by itself. So in other words, I would just divide by 2 on both sides here, and I will switch to x. So sine x cosine x. By the way, hopefully you recognize this double angle formula from your trig class. Sine x cosine x, I'm dividing by 2 on each side, so it's sine of 2x over 2. Okay, so that's how we refreshed some useful trigonometric identities that we'll need. And also you can use this page as the reference for you as you solve trigonometric integrals. And now we're going to do examples and see where exactly we use these identities.